Hello students, welcome to my channel MS Maths. Uh, Today we will discuss about the theorems and examples for exercise 3.4, and in previous videos we discussed everything related to exercise 3.3 and also we solved exercise 3.3 all the sums. So please go to page number 133 and point number 3.5. Point number 3.5. In which there is written prime numbers and their properties. So before we go to prime numbers and their properties, we have to understand, we have to know clearly about prime numbers and composite numbers. What is prime number and what is composite number? If we don't know, if we don't understand clearly about prime numbers and composite numbers, so we will have difficulties to understand the properties and theorems and examples. So here in the book itself it is written the definition which I have written here, that what is prime number, the definition is given. What is composite number, the definition is given. For prime number, an integer p is greater than 1 is said to be a prime number if p has no divisor other than 1 and p itself. So as we all know about prime number, because in our school life, from lower classes onwards, we have been learning always prime numbers and composite numbers. Just it is a recall. It's a recall only that which are called prime numbers. That means it's a refreshment only. So we understand, we know actually what is prime number, but we will know it now very clearly. Suppose, for example, number 3. 3 is a prime number, that we know already. 5 is a prime number. 7 is a prime number, that we know already. Why 3, 5, 7, these are prime numbers? Because 3 we can divide by 1 and 3 also we can divide by 3. 1, 3 is a 3. 3, 1 is a 3. So 1 and 3. 3 we can divide by 1 and 3 itself, not any other number. Only 3 itself and 1. So 3 is a prime number. If 3 could have been divided by any other number, then we cannot say 3 is a prime number. As 9 is not a prime number. Why 9 is not a prime number? 9 we can divide by 1. 9 we can divide by 9. And 9 also we can divide by 3. We have got 1 divisor, 2 divisor, 3 divisors. 3 divisors, since we have got 3 divisors or divisor, whatever you can say, 9 is not a prime number. So a prime number must have 2 factors. A prime number must have 2 divisors. 1 and itself the number itself. Then only that number will be called prime number. So 9 is not a prime because it has got 3 divisors. 1, 9 and 3 extra. 3 is extra. 1 and 9 it's okay. But 3 is extra. Or you can say like this, 9, 1, 3. 9 has got 3 factors. 1, 3, 9. So it is not prime. It is not a prime number. Suppose similarly 5. 5 we can divide by 1 and 5 also we can divide by 5. So 1 and 5 only. 7 also 1 and 7 itself. So that is why 3, 5, 7 they are called prime numbers. And this prime number must be always greater than 1. So this is the main part, 1 and p itself. P is a prime number which is greater than 1 and it has got 2 divisors, that 1 and p itself. So let us go to composite number now. Composite number, just m is taken as a letter, that's number, that m is greater than 1 is said to be a composite if it is not prime. If 3 is not prime, so 3 will be composite. 9 is not prime, so 9 is composite. So 9 is composite. Why? Because 9 is not prime. So all the numbers greater than 1, they will be either prime or composite. but this should be always that is greater than 1. The thing is that if the number is not composite, then prime. If the number is not prime, then composite. That is first preliminary part. Second part, or m greater than 1 will be a composite. That means m will be a composite if there is an integer p such that p is greater than 1 and p is smaller than m. And p is a divisor of m. So let us go to 9 only. 9. 1, 9 and 3. M will be a composite. M means 9. If there is an integer p, this is p, such that p is greater than 1. What is p? 3. 3 is greater than 1. If 1 and 9 itself, then 9 could have been a prime number. So it has got one more factor, or it has got one more divisor. So that is p. P is a divisor of m. P is a divisor of m. That means by p, that means 3. By 3 we can divide 9 also. That 3 is smaller than m. M. What is m? M is 9. M is 9. So that p, that number, always greater than 1 and smaller than 9. That p will be, so we can write this way now. The condition, no? That condition, this condition is there. This condition exists for composite number. So p, whatever number we get extra, that should be greater than 1 and that should be smaller than the number itself. That means that m is what? What is m? M is composite number. M is composite. This condition you have to remember. And that is actually when you get the numbers, then automatically it comes out, no? So 3, suppose 10. Suppose 10. 1, 10, then 2, then 5. By all these numbers you can divide 10. So 10 has got 4 factors. So anyone, 2 or 5, anyone can be taken as p. This is m. Either 2 or 5 we can take as p. What is p? P should be always greater than 1 and p should be always greater than m. So whatever extra factor we get, that should be greater than 1 and less than m. This is m. P is 5, suppose. So it is very clear what is prime and what is composite. So please take it very seriously about the definition of prime number and composite number with examples. With examples. If number, any number, if we cannot divide by any other number rather than the number and 1 itself, sorry, 1 and number itself, then that will be prime number. Any number, 19. 19 is prime. Why it is prime? Because 19 we can divide by 1 and 19 itself. 19 is not divisible by any other number. So 19 is prime. 23 is prime. Why 23 is prime? Because 23 we can divide by 1 and 23 itself. 24 is composite because 24 we can divide by 1 and 24 itself any other number also. 12. 6 for the 24. So by 6 we can divide 24. By 4 we can divide 24. So 24 is a composite number. So in both the cases, p is prime greater than 1. M is composite greater than 1. So whether it is prime or composite, all the numbers must be greater than 1. So what? 1 is neither prime nor composite. So remember always this. 1 is never be prime or composite. 1 is neither prime nor composite. Because prime number, whatever is p or 5 or 3, whatever, that is greater than 1 and composite also greater than 1. So 1 is neither prime nor composite. I hope you understand. Now theorem number 9. If P is a prime number, A and B are two integers which P divides AB, then either P divides A or P divides B. This is what we have to prove. Actually, if P divides AB, then since P divides AB, that means A into B. So surely P will divide A or P will divide B. Because it is like this, 3 divide 18, or we can write 3 divide 3 into 6, like AB, no? 3 divides AB. So 3 will divide A, 3 will divide B also. And sometimes it is like this, 2 into 9. 2 into 9 is actually 18. 3 divides 18. But 3 divides 2 into 9. Either 3 will divide 2 or 3 will divide 9. This is what the meaning of this theorem. Either 3 will divide 2 or 3 will divide 9. 3 or either or. If it is 3 and 6 both, 3 will divide 3, 3 will divide 6 also. Now here 2 into 9 is 18. 18 is divisible by 3. But either, so either or. Here either or comes. So this is what you have to understand. So here, so actually there is nothing to prove. But that is why we have to take let P does not divide A. P does not divide A. If P does not divide A, then P is not a factor of A. If P does not divide A, so P is not a factor of A. So it is like this, 9 does not divide 8. By 9 we cannot divide 8. So no factor. 2 divides 8. Yes, 2 is a factor of 8. But 9 we cannot divide 8. So 9 is not a factor of 8. Because we cannot divide. I hope you understand. So P is not a factor of A. Again, here there is written, it is given that P is a prime number. Since P is a prime number, so it has two factors. What are they? 1 and P itself. Since it is a prime, because in the previous we have understood that what is prime number. 1 and P itself is a prime number. So since P is a prime number, so it has two factors, 1 and P itself. So now GCD, theorem number 4, page number 116. Page number 116. There is a theorem for two integers A and B, at least one of which is non-zero. There exists another two integers X and Y such that GCD of AB is equal to AX plus BY. So here GCD of P and 1. P and 1 is 1. Why GCD of P and 1 is 1? Look here. For P there is two factors. One is 1, other one is P itself, because P is a prime number. For A, P is not a factor of A. So what is A now? Let us see A. Surely 1 is a factor of A, but P is not a factor of A. Why? P is not a factor of A. Already we have taken. Let. So greatest common divisor GCD of P and A will be 1. Because P no common. Here P is not a factor of A. Here it is written. So for A, P is not a factor. For P, 1 and P both are. So between P and A, what is the common? 1. So GCD of PA is 1. So in place of GCD of PA, what can be written? This is theorem number 4. GCD of AB is equal to AX plus BY. This already I explained. I hope you understood it when I explained it. So GCD of AB is equal to AX plus BY. So here PX plus AY is equal to 1. I hope you understand. AB, AX plus BY. PA, PX plus AY. So this is number, this we can write from theorem 4 we can write. PX plus AY is equal to 1 from theorem 4. That we can write. Now what we have understood? Now we can do one thing. We can multiply each term by B. P Bx by M in plus A By is equal to B. Why we have multiplied each term by B? Because we need B also. Here B is missing. A already we have taken that P is not a factor, that is finished. So now B is missing. A is there. There is no B. A is there. P divides A or P divides B. A is present here. But B is not present. B is missing here. So each term, both sides we have multiplied by B. So we have got PBX plus ABY equals to B. Suppose this is number 1. Now, by looking this term, we understand this whole term or PB. P divides PB. PB will be surely divided by P. Look at here. 3 into 6. P into B. 3 into 6 will be surely divisible by 3. Of course, it is 18. 3 into 6. 18 is written in 2 parts. 3 into 6. So this 3 into 6, will it be divisible by 3? Sure, because 3, here also 3. So 3 1 3 like this we can do. Anyway, so 3 into 6 is divisible by 3. That means what? 3 into 6. Think like this way. 3 into 6. PB, P and P. P is divisor and P is dividend. So by P we can surely divide PB. And P divides AB. It is given. P divides AB, it is given. P divides PB, we have got from here. P divides AB, it is given. So it is written AB. So now this and this are related to theorem number 3.7. Page number 113. Page number 113. Theorem number 3.7. If A divides B and A divides C, then A divides Bx plus Cy. Where x, y are local. A divides B, A divides C, then A divides Bx plus Cy. Which B, x will come, which C, y will come. Same thing. P, look at this one. A divides B, A divides B, A divides C, A divides C, then A divides Bx plus Cy. Here, P divides, this is A, this is A. P divides PBx plus ABY. With first term x is included, with second term y is included. With first term bx, with second term y. Okay, so P divides PBx plus ABY. PBx plus ABY is equal to B. So P, in place of PBx plus ABY, we can write B. So P divides B. Finish. The proof is finished. If P does not divide A, so P divides B, we have proved. So if we write here P does not divide B, then we can prove P divides A. So vice versa, no? Simultaneously we can do this. So from this we can write that P is a prime number, A and B two integers. If P divides AB, then either P divides A or P divides B. If P does not divide A, then P divides B. I hope you understand. So if in place of A, if we write here B, then we can conclude at A. So therefore, we can write this. So this is written only in the book. I hope this one you understand, GCD. This one already I explained. This is also I explained in previous classes. A divides B, A divides C. So P divides PB, P divides AB. This first one is same. So with PB, X comes, with AB, Y comes. Like this one. So I hope this you have understood clearly. Then there is a corollary tree. If P is a prime and A1, A2, A are any n integers, with P divides A1 into A2 into A3 an, then P divides AK for some K1, 2, 3 n. So it is very simple. That means this one is multiplication now. P divides any multiplication A1, A2, A3, An are any integers. So multiplication, suppose it is like this, 1 into 2 into 3 into 4 into 5, like this it goes on. So this P is a prime number. So multiplication, whatever it is, suppose number is 3. Suppose 3 is a prime number. By 3 we can divide this or not? Because here 3 is present. Here 3 is present, so it is divisible. So 6 is also present, so it is divisible. 18 is present, 3 6 is 18, so we can divide. The multiplication we can divide by 3 also. Same thing here also, corollary 4. If P, Q1, Q2 till Qn are all primes and P divides Q1, Q2, Qn. Q1 to Q1. This is multiplication. This is multiplication. This is not multiplication. P, Q1, Q2, all are primes. P to Qn, all are primes. And P divides, this is P. P divides rest of the numbers. Yes or no? Rest, multiplication of rest of the numbers. Then P equals to Qk for some K, where K equals to 1, 2, 3 till n. So Qk, Q1, Q2, Q3, Qk. What is K? 1, 2, 3. 1, 2, 3, 4, 5, 6, like this till n. Till n. So, NP divides Q1 into Q2 into Q3 into QR into Q5, like this till Q1. Multiplication, this one. P divides multiplication of rest of the numbers. Then P equals to Qk. Qk means this one. What is Qk? Q1, Q2, Q3, all are Qk. Qk means, so P 1, 2, 3, suppose 5 numbers are there. Suppose 5 numbers are there, it is 3. 3, then 5 numbers, any 5 numbers are there. So by 3, all this multiplication will be divisible because these are all prime numbers. Because these are all prime numbers. This is prime number surely, these are also prime numbers. Multiplication of these will be divisible by 3. Then P equal to Qk. This is corollary number 4. This will be applicable in different sums of the exercise. Example number 1. Example number 1. Express 36,000 as product of primes. So it is very simple actually. Just 36,000. Just go on dividing by prime numbers. 2 18 is 36. 2 9 is 18. 2 into 45 is 90. 2 into 2250. 2 into 11 to 5, 2 11 to 22, 2 to the 4, 5 to 12. Then this is not divisible by 2, so it starts surely trying by 5 only, because last digit is 5. 5 2 is 10, 5 2 is 10, 5 5. So 5 like this, 5 9 is 45, 3 3 is 9. So these are all prime numbers. Express 36,000 as product of prime numbers. So we can write 36,000 is equal to 2 to the power 1 2 3 4 5. 5 into 1 2 3 into 3 square. So these are all prime numbers. So this is very simple. There is nothing to understand here. Example number 2. Examine whether 509 is a prime or a composite number. So P be the list of all R. So there was a theorem. There was a theorem. The theorem number 12, page number 135. Theorem number 12. Let n is greater than 1. If n is greater than 1, be any composite. N is composite, okay? Composite. This is the theorem. Theorem number 12. And Q be the list of all divisors. Q list of all divisor. List of all divisor means suppose 16. 61, 16, 2, 8, 4. So these are all factors, no? Or divisors. 1, 16, 2, 8, 4. These are all divisors. Because by these all the numbers we can divide 16. So Q be the list of all. So among this list, which is the list? This one is the list. So like Q, no? Here we have written Q. So 2 is the least of all the divisors. 16 is a composite number. Among these all divisors, 2 is the least of all. So Q, if the Q is the least, then according to theorem, Q is smaller than square root of n. What is n? N is composite. That means 16. 16. So from this is the theorem. Okay. Q is smaller than square root of n. N means here 16. Q means 2. Q is smaller than root n. N is 16. Here composite number. 2 is Q is least divisor. Least divisor among them. So 2 is surely smaller than 16 because root 16 is 4. So 2 is smaller than 4. So that is okay. So this is the condition. This is the condition for composite. So examine whether 509 is a prime or composite. So we will see whether it is composite or not. So to see, square root is there. Since square root is there, if P be the least of all integers, divisor and 509, then P will be, for composite, P will be smaller than square root of 509. Square root of 509 we will try to find out. What is P? We will, that is the composite number. Sorry, P is the list of all integers. P is the list of all integers, sorry, all divisors, and which should be smaller than square root of 509. I think square root of 509 is found. Okay. Let us find out square root of 509. That you know, all of you. This way. 2 into 2 is 4. 1, 0, 9 will come down together. That you know already. And it is 4. 2 to the 4. 2 4 is 8. 5, 2. 25 is remainder. That means 22. This 509 in between square root of 509 will be surely between 22 and 23. So if we go on divide like that, it will be decimal something, 00, then we will go on dividing. So 22 point something we will get here. Square root of 509 we will get 22 point something. That means what? Square root of 509 will be between 22 and 23. 22 point something we will get here. We are not going to finish up the what is called square root, because we are trying to getting the idea. We are trying to get the idea. Square root of 509 is greater than 22 and smaller than 23 because we have done the square root. Square root of 509 we will get here 22 point something. So sure we have got that square root of 509 is will be between 22 and 23. So the prime numbers less than 22 are. So less than 22 prime numbers will be 2, 3, 5, 7, 11, 13, 17, 19. No? Yes. So therefore, if 509 has any prime divisor, then it must be one of the numbers. But it can be verified that none of these primes is a divisor of 509. Thus 509 is prime number. So by 2, if we try to divide 509, this 509 just by 3, no, by 5, 5 10 is 59 is left. 7 7 is 49, 11, 44. So if we try by these all the numbers separately, if we try to divide, then this will not be divisible. Less than 22, whatever numbers you list, list, because for composite list it is not divisible. List divisor, it is not divisible, so it is not composite. Now we will see that those less than 22, whatever composite, prime numbers are there, if among these prime numbers anyone can divide this, then 509 is not prime also. But surely 509 is prime because it is not divisible. Among these numbers, all are not divisible. 509 is divisible by 1 and 509 itself, because then only it will be prime. If among these numbers, suppose by 19 we could divide 509. Suppose 509 is divisible by 19, we will get remainder 0. Then 509 will never be prime. Among these prime numbers, by anyone, if we can divide 509, then 509 will not be prime, it will be composite. But we have seen that we can assume here, I could understand that. We can try also one by one, that by 13 it is not divisible, by 17 it is not divisible, by 19 it is. So among all these numbers, if we try to divide 509, so this will not be divisible. So 509 is prime. Whether we have to examine whether 509 is prime or composite. So 509 is prime, because 509 is divisible by 1 and 509 itself. Next, example number 3. Find all prime divisors of factorial 50. What is the meaning of factorial? This sign is factorial. Factorial 5, it means 5 into 4 into 3 into 2 into 1. This is the meaning of factorial 5. Means factors from 5 backwards. 5, 4, 3, 2, 1. Factorial 8. So 8, 7, like this. So factorial 50 means 50 into 49 into 48 into 47 into 3 into 2 into 1. This is the meaning of factorial 50. What we have to find out? Find all prime divisors of factorial 50. Prime divisors of 50. That means from 50 to 1, which are the prime numbers? That is what we have to find out. So from 50 to 1, we can find out all prime divisors. 1 is not prime, neither prime nor composite. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. I think this must. You can check it, no problem. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43 and 47. Therefore, all these numbers are divisors of, prime divisors of factorial 50. That means this multiplication will be divisible by 29. This multiplication will be divisible by 37. So these are all prime factors, prime divisors. Divisors means we can divide by this. Factorial 50 can be divided by any of this. This is the meaning of this example.